Good morning, good afternoon, everyone, and welcome to today's monthly program of ARA Webinar Wednesday. I'm Jerry DiMaggio. I'll be serving as your moderator for today's webinar, which is entitled Risk-Based Asset Management for Geotechnical Features, or also known as GAM. Next slide, please. I'd like to first cover a few housekeeping items with you. If you're experiencing an issue with your sound and you're using your computer speakers, turn off your speakers and dial in using your phone. If you continue to have an issue, please use the chat button and send a message to our host. Next slide, please. We encourage you to ask questions throughout the entire program, and those questions will be addressed at the conclusion of the technical program today. If you have questions, and please listen carefully to the directions that follow, please click on the Q&A button to send your question, and we will address these questions at the Q&A sessions directly after the presentation. Send your questions, the Q&A, to the host and to the panelists. Do not use the chat button to send your questions. Next slide, please. Finally, to view the presentation in full screen mode, at the top of your webinar settings as shown on this slide, click on the down arrow, highlight View, and then choose Fit to Viewer. Now it's my pleasure to introduce today's speaker. But before I do that, just a brief reminder, everyone will receive a 1-hour PDH certificate if you attend the entire 1-hour full session. And we keep a record of that, so please be patient and stay with us for the entire hour. Next slide, please. Finally, for my introduction, I'll moderate the Q&A session at the conclusion of the technical program as well. It's my pleasure to introduce today's presenter, my very good friend and colleague, Dr. Ahmad Al-Hassan. Ahmad is a senior research engineer and a team leader at the Research and Technology Deployment Group at ARA. He specializes in infrastructure evaluation, risk-based geotechnical asset management, probabilistic performance modeling, and risk-based transportation infrastructure management. Ahmad is leading a wide range of projects currently in pavement surface characterization for both highway and airfield applications, geotechnical asset management, non-destructive evaluation, and infrastructure performance modeling and management. He's authored and co-authored more than 40 technical articles in journals on a variety of topics. And now I'd like to turn today's program over to Dr. Al-Hassan. Ahmad.
Thanks, Jerry, for the introduction, and I'm pleased to share my presentation and discuss geotechnical asset management today with all of you. So here's the outline or the agenda for today's webinar. We will talk about these different topics, and one thing I will do throughout the presentation is I'll go back to a hypothetical example that we applied some concepts here to basically emphasize on how these procedures or some of the procedures will be performed. Another thing to point out that these items on the agenda are not necessarily sequential in all GAM programs or geotechnical asset management processes. These are just some of the highlights that we would like to discuss today. So a lot of processes and procedures could be done in between. So the first item to start with is basically the place of geotechnical assets within transportation infrastructure asset management at large. So asset management in general, as you probably already know, is basically a systematic process to maintain and upgrade the transportation assets that we have. So it helps keep things performing well, given the stringent budgets available nowadays and the evolving and growing network that we have in the US especially. So asset management helps optimizing and at least prioritizing the processes to keep up with the demand for transportation networks. Another thing I wanted to point out here is basically that asset management builds on multiple disciplines and comes from multiple directions. It tackles the problem through economic theory application, decision-making processes. So we will always go back and refer some of the fundamental processes and theories behind engineering, transportation, asset management. Which geotechnical assets are we referring to when we're talking about geotechnical asset management programs? So that term, geotechnical assets, can be a little bit wide, and it depends on the agency, what they want to define for geotechnical assets. So it could include retaining structures, embankments, slopes, foundational elements of other transportation assets, such as bridges, for example, tunnels, culverts, are all possible geotechnical assets. So more generically here, we're talking about geotechnical features. That's how we would think of geotechnical assets at this stage. But the final conclusion on which assets to include, that depends on the agency and the goals of the agency, and we'll talk a little bit about that. So here is a general outline of the geotechnical asset management process. So this process here comes from the NCHRP project 24-46, and this is more of an implementation process or implementation steps for GAM programs. So today we will tackle some of these processes, but one thing I wanted to point out in this slide, as I mentioned initially, that the progression in these processes depends on the agency needs and the agency level of maturity. So some agencies may realize that they have a humongous database that they have been collecting, for example, for a tangent application, let's say, to geotechnical asset management, and then now it's time to implement geotechnical asset management, which means that this agency may skip basically the first, for example, 1 or 2 steps in the process and really go into the third process. One other thing I would like to point out is it is important to think of all these processes before even starting a GAM program. So keeping in mind what you need in each step is important for you to basically optimize or maximize the benefits out of these steps. So starting with a data collection program that you're not sure about what type of performance models you will have can be less effective and may require the agency to go back and collect more data. And for that, the first step or the first general step, and again, the first step would be thinking about what you need in a GAM program maybe, but the next one would be to start collecting data. Data collection is important and significant, and there are a lot of technologies out there. However, for geotechnical applications, there is still a debate on what to collect and how to collect data. So far, there are some applications where there's a LiDAR database, for example, for multiple assets out there. But the question is, do we need the entire LiDAR database? What exactly is important in that database? How to organize it? All of that should be thought of early on in the process. One other aspect would be defining the assets to be included in the database. So for example, not only answering is it a retaining wall or a slope, but how big the retaining wall to be considered in a GAM program. Should we consider all retaining walls regardless of their size? Should we look at the size of the retaining wall? One good aspect or idea is to use risk assessment or the concepts of risk assessment in that process. Look at the risks associated with these walls. For example, small retaining walls throughout the state that are low probability, but they are extensive in number. So eventually they could fail, and their consequences may not be as dramatic, but from a budgetary standpoint, they can lead to some complications. So risk-based data collection is important. There is a lot of advancement in technologies. Remote sensing is available out there, but there is still a lot to be done on what to collect and how to properly collect that data. And again, rehashing the point of asset inventories and data management, it is very important to think about data management and data governance. And the data governance terminology is a little bit more broad that includes what to collect, how to collect data, how to keep the data resilience itself. Like, is your database resilient? If someone changes or the knowledge structure changes within an agency, is that data reusable in the future? And all of these are points that could be studied or accounted for early on in the process, but need to be dynamic and will be updated as the GAM program grows within the agency. Now that we have talked about the geotechnical features in general and their aspects within transportation asset management, condition evaluation would be the next big question to ask. So how do you assess condition of geotechnical features? Up to this point, there are different approaches available out there. There's, for example, visual inspection processes out there for agencies. They have manuals on how to inspect certain assets, for example, for culverts, for retaining structures. Not all agencies at the same time have these manuals or procedures, not necessarily, but visual inspection would be one approach to do it. Another approach would be to acquire actual engineering measurements in the sense that they measure, for example, strength, deformations, or other properties, in situ properties. Regardless of the process that will be followed, and each one, by the way, has an advantage and a disadvantage. Visual inspection for the first site could be like, this is not real engineering measurement, or this is not actual measurement that you could rely on. However, when we're talking about network level applications, it might be the most viable solution out there. But going back to the concept of risk-based data collection, and you will hear me repeat the terminology risk here over and over, one approach would be to assess the risks associated after visual inspection. So for example, if you have an asset that has been there for a while, it's showing a lot of deterioration at the surface, it may be smart to go back and collect engineering measurements and more in-depth inventory. But at the network level, a visual inspection may be the procedure to follow at this stage, as long as we have limited engineering measurements to collect at this stage. However, there is a progress in non-destructive valuation, and that would eventually help in improving that assessment at the network level and at the project level. So there are a lot of technologies out there that are being assessed now. A lot of them have been assessed and proved to work, but also the question comes, how useful is that for your GAM program? There's, for example, a condition evaluation procedure that depends mostly on visual inspection that was developed for MSE walls. And the reason that we're mentioning that, because MSE walls are extensively used and they show sometimes accelerated deterioration. So as you can see to the left, to the far left, there is basically the list of items to look at or inspect during a visual inspection or an engineering measurement. So this is a generic process here that can incorporate both, actually. But it was originally developed for visual inspection in general, and some simple measurements. Now, after that, the most important aspect is to come up with a system as well. First of all, that is consistent in the evaluation process for each individual item on this list, but more importantly also to transfer that into a condition rating or a scale. So you may end up with a scale from 0 to 10 where you define, for example, each step on that scale or each condition state on that scale and what it means. And also the other important aspect is to come with an overall measure or overall performance measurement that can summarize the performance of the geotechnical asset that you have. Now, the procedures to come up with these weights, for example, here at the top, we're talking about the weight for each condition rating within these 3 boxes. So you come up with a condition rating for box 1, box 2, and 3. You multiply them by weights, and then you divide them by the total relative weights. And that can give you an overall performance measurement that could be on a scale from 0 to 100, for example. That is a more fine scale or discrete scale. And you can also transfer that into a more aggregated scale of poor, fair, good. as shown to the right of the screen here. So there are procedures to come up with basically relative weights and so on, and that would be very critical when it comes to geotechnical asset management. The next point would be basically looking at the overall network performance. Even though here the plot shown to the right, the histogram, makes sense. You collect data for a bunch of geotechnical assets or features, and you summarize the condition rating, for example, on a scale of 1 to 5, and then you summarize it for the network. That is intuitive, but what I wanted to point out in here as well is the concept of propagating from an individual asset level to the network level in terms of condition evaluation and performance predictions, and we will talk briefly about that throughout this presentation. So the concept of propagation is basically that the overall network performance should account for the individual assets. And even though the statement sounds very intuitive, very trivial, but sometimes what happens is when you summarize at the network level, you lose track of the individual assets. And that's understandable given the complexity of keeping track of the individual assets. And that would affect basically performance or improvement plans that we will talk about towards the end of this presentation. So keep in mind the concept of propagation, start from the individual asset, and collectively that would give you the performance at the network level. Keeping track of that connection is important when it comes to basically improvement plans. Another aspect also of the network performance is to look at the impact of condition at the network level on the overall network performance. So these are two separate things. The previous slide, we were talking about the physical condition of the assets collectively. But now we're talking about the impact of these assets on the ultimate goal of the network. For example, safety, reliability of the network, and other aspects related to missions, for example. So the physical aspect here to the top right corner in this example is talking about bridges, for example. This is the physical condition, and this is one aspect. However, that would eventually affect also highway safety, emissions, reliability, and a lot of other things. And these network level measurements are not only affected by geotechnical assets, obviously. Geotechnical assets is just one component of the network that includes pavements, bridges, and many other assets as well. So assessing the impact of the geotechnical assets on the overall network performance is also an important aspect to keep in mind. Now that we've talked about the condition evaluation process and so on, performance modeling would be the next step. So the difference between condition and performance, and that definition, by the way, varies from agency to an agency and from basically one person to the other. Performance can be defined in one of the definitions is basically the condition over time, how that condition is changing over time. Condition is the instantaneous condition of the asset. Once you go out, look at it, that wall is in a good condition. But how would that perform over time? That's what we would refer to as performance record here in this presentation. So performance records can be discrete. Again, if we have a visual inspection process, then it will be discrete in nature. However, keeping in mind that the degradation process is a continuous process is important from the modeling aspect. So even though you're not required to keep track always of the continuous degradation over time, maybe, and you may report on a discrete scale, keeping in mind that the degradation process in the background is continuous is an important aspect when it comes to modeling, and we will show that briefly here. And the other one is basically that the degradation rate will most probably change over time. Some assets start with very accelerated degradation at the beginning and then slows down, or it could start slow and then accelerate in the middle and then slow down again when it reaches a very bad condition. So slowing down is not a good thing towards the end because you've already exceeded a certain level of performance requirement and the asset would be in a bad condition state. So here's an example of that continuous versus discrete and how it would affect the deterioration models that we have. So for example, here's a deterioration process or data that comes for culverts actually from a project that we have performed previously. So the culverts were rated on a scale from 0 to 9 on condition scale. And we have summarized the data versus age for each culvert. As you can see, the triangles here on the screen represent the actual measured data. And these are obviously discrete. They have basically platoons and horizontal lines reflecting basically condition of multiple culverts at multiple ages. But if you average these readings for each year on the age scale, you will have a smoother process that is shown here. Now, that smooth process is not the same as the continuous degradation process. This line here represents the average overall performance or the expected value of that deterioration process. So, following on that, deterioration models, for example, that you could use can be discrete in nature, but keeping in mind that the continuous process in the background and you're discretizing the domain of condition that we have, for example, 0 to 9 or whatever condition state, is important when it comes to assessing these probabilities. So you should understand that when we're doing deterioration models, there is a probabilistic and uncertain nature, and part of that comes from that discretization process. So in 1 year, it may look bad, for example, and sometimes, and it happens all the time, and we've seen it in databases over and over, that an asset may go back a little bit to an improved condition state. Did it really improve over time? Definitely not, but from a visual inspection standpoint, and since we have discretized the domain, you may end up with a dispute in the definitions. And the same person that went out evaluating in 1 year maybe come back next year and look at the asset and it looks better, cleaner, for example. Maybe it's not real engineering maintenance to a point that it improves the structural capacity, but it could be some kind of maintenance or not even maintenance. It may be a cleaner asset at the second year, and that would bump it back up to an improved condition state. So these deterioration models, for example, there's the Markov chain model that we used actually for our hypothetical example. So our hypothetical example includes a network, a small network of slopes, and these slopes could be basically a different type of slope. We didn't really identify anything in here. It's just a general hypothetical example. And here is basically a deterioration model for that. As you can see, we have a continuous line reflecting the expected value over time. The expected value is not the most probable condition state, because the most probable condition state should be discrete. It's either 1, 2, 3, 4, or 5. But the continuous process is basically where that distribution center settles. As we have seen previously, there is that distribution, the histogram. The center of that histogram would fall on this line. So this is the deterioration model that we have used for our hypothetical network and how it changes over time. One thing to point out that the deterioration model used in here looks a little bit closer to a straight line. However, the deterioration process is not like that. And that is one attribute of the Markov chain models. So Markov chain models, if we use them as they are typically used in infrastructure applications, you only allow an asset to stay in its own condition at a certain time step or degrade to the next worst condition state. One thing that we have tried previously is actually to redefine that probability distribution, allowing some of these assets to go back again to an improved condition state. So that probability, even though it's small, it is still available out there. And allowing for that in the Markov model, again, that follows from the understanding that this is a continuous deterioration process and the discrete condition scale is not basically the ideal engineering representation. So understanding that aspect and allowing some assets to go back to an improved condition actually improved our deterioration models and increase the flexibility of the deterioration model to allow for that nonlinear behavior in one model. So the conclusion out of this in terms of deterioration models, keep in mind the process in the background and try to maximize the benefits out of the deterioration models that you have. Look for other alternatives in deterioration models and how they can actually adapt for your data. Now, once we have, again, that deterioration model for individual assets, let's look at how that would affect the overall network condition. As I mentioned, the idea of propagating models from a asset level to network level is apparent in here. So in here, we've took basically our hypothetical network and looked at the network condition after 5 years, for example, with no action. That could lead to a distribution, and it should lead to a distribution there since there is uncertainty in our predictions. So for example, here you can see that we have distribution for the percent poor, fair, and good for basically an asset after 5 years, or a set of assets in that hypothetical network. Also, when we did the analysis, and we will talk briefly about the improvement plans, we looked at the possibility for a treatment, and we looked at how much that treatment would start shifting the distributions. So if you start shifting the distributions, then you can basically look at the value of the treatment in a more realistic fashion, including the distributions, knowing that there is a level of uncertainty. And after 5 years, you're not necessarily going to see exactly the value that you've predicted for example, percent good or fair or poor. There will be uncertainty associated with that prediction. But what you want to do within any asset management program is to maximize the likelihood of reaching that improved condition state. And since we have talked about uncertainties a lot, risk management comes in role here, and especially quantitative risk management. So what really defines risk is also a discussion for probably another presentation. But what we want to come out with here, that uncertainty or risk relates to the uncertainty to meet an objective or a goal. It could be positive or negative, and that also a debatable definition. Should we include the positives within the definition of risk? There is a positive uncertainty for sure, but should that be included in the risk assessment or not? And that would lead again to impacts on objectives. You have uncertainties, you're not 100% sure how you will achieve that goal, and that would reflect basically on your ultimate goal after a certain period of planning. Some of the sources of uncertainty here that relate basically to GAM programs is measurement uncertainty. We've talked about condition evaluation. We've talked about collecting visual inspection data. There is uncertainty related to that. The deterioration process, our understanding of that process, there is uncertainty as well. And that's why I say that when we were talking about the deterioration process and the inspection actually, is basically engineering measurements, even though are very valuable, they are not necessarily always the final answer, because these by themselves have uncertainties associated with them. They are definitely better than visual inspection if they are well established, but they can be also very costly and time consuming. So visual inspection could be an alternative, but the conclusion is basically there is uncertainty in both evaluation procedures because there is uncertainty or limited understanding of the deterioration process and the conditions surrounding these assets. And there is also uncertainty in the external effects, extreme conditions, change in the environment, and change basically in the traffic levels that required basically these geotechnical assets are required to hold and support. So all these are some kind of external uncertainties. Again, this list can grow, but these are the main overall types that we can talk about. So when it comes to geotechnical assets, people have looked at risk, but in terms of failure, of total failure. So risk was defined, for example, in terms of cost. What is the cost given the probability or the expected cost for a given asset that will fail basically in 5 years. And as you can see to the right, this probability of failure is related to condition state. And this is how you assess the risk. So if you have an asset, for example, at condition state 2, let's say, then you have a probability associated with that condition, with that asset, that it will fail with that much probability. But guess what? When you forecast into the future, where would you be in 5 or 10 years? Would it be at 3, at 4? That makes a huge difference. And that complicates the analysis. When we're talking about quantitative risk analysis, there are complexities that when we're forecasting, there is uncertainty with the forecast. There's uncertainty associated with the data collected, and there is uncertainty in the probability of failure. So that's basically different sources of uncertainties that come in role. So here, for example, there is another type of uncertainty, not necessarily risk of failure, but also the risk of reducing the performance, serviceability uncertainty, or serviceability risk. So there is a risk that a given pool of assets here at 10, some of them would drop to fair, some of them would drop to poor in 5 years. And understanding and quantifying these risks would help you basically prioritize your selections. And that leads us to the next topic, how to select some kind of list of assets to fix. And again, this is not the final answer, and this is not the most extensive approach, but we're talking about the basic fundamental concepts that will help us get there, hopefully. The first aspect relates to treatment impacts. When we're talking about improvement plans and investment strategies, it is very important to understand how preservation and maintenance activities affect condition over time. And also, understanding the uncertainties associated with that is an important aspect when it comes to planning. So the plot here is a very generic plot, comes from basically, this is a collective plot that comes from many asset management studies, showing the benefits of preservation versus basically, or having some kind of effective maintenance and preservation program versus the idea of worst first approach. Wait for the asset until it reaches a bad condition and you go ahead and try to basically improve that. That strategy in here can get you to very bad condition, and the cost associated with reconstruction can be much, much larger than the cost of preservation. So having kind of prioritized approach or more systematic approach to identify the assets to fix is very critical. Now here is going back to our hypothetical example. Here is a table of the assets that we have, again, condition states, and by the way, this table continues to include many other assets. So let's say we have a group of assets, the first 7 assets have a condition state of 5 in this year, and so on, and it drops to 4, and again, the table continues dropping to lower condition states, or other condition states, and that relates basically to the probability of failure, okay? So each condition or each asset would have a probability of failure and an expected cost. So if it fails, how much would it cost? So multiplying the probability of failure by the cost when it fails would give you basically an expected cost, here shown in the column. And then that would add up to an expected total cost if you don't do anything, for example, in 5 years. Now the next column basically is the decision column. And that decision column here is basically, okay, let's say that we're going to make some improvements to asset number 2 and asset number 5, basically, and you select some assets, and you start seeing how much that cost, total expected cost of failure, would reduce. And that, the number of assets to be fixed, can be basically constrained by the budgets, and that would be one of the constraints, or it could be constrained by other elements. Now, the important aspect I wanted to point out here is basically the use of Monte Carlo simulations. As I've mentioned, predicting the performance in the future has a probabilistic nature by itself. So the column in here, the second column, shows the condition state at the first year. However, the future predictions would have a probability distribution, and it won't be a single point. And each condition state would have an associated probability of failure. And accordingly, the expected cost would be a more complex distribution that accounts for both uncertainties. Monte Carlo simulation is one of the simplest approaches relative to basically closed form approaches that are sometimes not feasible. So you run the Monte Carlo simulations in some sense to assess the overall uncertainty in the expected cost and come up with basically a distribution for the total cost. So the total cost in here, if we click on it and basically the tool that we have developed, you will find a distribution of total cost behind the scene, and that comes from the distributions of basically predicted performance and predicted probabilities of failure. Now that we have these scenarios, the previous table showed one scenario, for example. We've selected a bunch of assets that we will fix, and we've looked how much reduction in the basically expected failure cost you have, or the difference or return on investment. That would be one return. But at the same time, you can assess the risk, the uncertainty associated in the future condition after improvements. So if you plot return versus risk, as shown here, one would expect basically a domain of solutions. Each point in here, or each circle with crosshair in here, includes actually a collection of improvement plans. So an improvement plan would include assets, and the assets, some of them would be fixed, some of them would be delayed for a following year, and that collectively gives you basically the return at the network level. And here comes the connection between the individual assets, the point that I've talked about at the beginning, the connection between the performance of an individual asset and the collective performance of the network. That is basically emphasized in the table that we have seen in this slide. So keeping track of that connection gives you these points. And when you look at that domain of return and risk, then you come up with a decision basically frontier, or what they call the efficient frontier. So an efficient frontier defines the strategies that gives you the highest return given a risk. So for example, if you move along the line Q here, the point at the top gives you the highest return, and the following point below it gives you also basically a reduced return, but at the same asset. So it would be a bad decision to accept a lower return in terms of improvements and accept the same level of risk. Alternatively, if you look at the horizontal line P here, if we look at the point to the left, that's basically a given return, but it has the lowest risk compared to the points to the right on the line P. So that frontier here is basically the efficient frontier and includes scenarios, a bunch of scenarios. It's not just one point, it's a scenario of basically improvement plans for the collective assets. One thing I wanted to point out that this process here is a little bit, let's say, fundamental. So fundamentally, you can derive something like that. But when it comes to decision making, this is just a decision support tool. Because in many cases, you may see that some of these solutions are not feasible. We don't have the contractors to perform the work. The time constraints, we cannot go out and fix that many. We have, for example, some other constraints outside the Geotechnical Asset Management Program that affect, for example, a community that we cannot go out and fix in this year. So that solution, even though on paper it looks as the best solution on that line Q, it may not be feasible. So keep in mind that all these tools are just support tools, and they should be dynamic and provide sufficient information to decision makers and help them make the right decision. So, for example, here we go back to our hypothetical example of a network of assets, and we have done some of that analysis. to assess basically the standard deviation in total cost of failure shown on the y-axis or the vertical axis, and the expected total cost of failure. Now, I've on purpose flipped actually the axes. So the expected total cost of failure is basically related to some kind of a risk here. And the lower that number is, the better your solution is. And the standard deviation relates to the uncertainty basically in the total cost. You want to reduce that standard deviation in the total cost of failure. You want to make sure that if I'm going to accept a given level in probability of failure, I should minimize that. So here the efficient frontier is actually in that lower corner. So the idea in here that this solution or this process of identifying efficient frontiers and looking at alternative solutions should not be rigid and should not be dealt with as basically given facts. This is a dynamic process. You may change the axes depending on what you're focusing on, and this eventually should be, again, a support tool to help guide decision makers. One thing I wanted to point out from this simulation, that we had multiple simulations, and you can see some of these form some kind of a bulb in there. So the simulation process itself gives you actually smaller frontiers. So don't be deceived when doing one run that this is the ultimate solution. So if you look at this cloud in here, it forms one solution. This cloud in here comes from another simulation, for example. Collectively, they give you a larger domain, and they can open your eyes to other alternatives that you couldn't see in the first run, for example, of simulations and analysis. Now, moving back basically to the big picture, we have dived a little bit into the technical terminology, looking at deterioration models, and basically some kind of optimization techniques. That there is a lot of work to be done there. Again, this is not the final answer, and this is not the optimal solution, but it's a process that we have went over. Let's go back to the big picture, challenges and future improvements that we can think of. The first one would be to come up with a harmonized condition evaluation for geotechnical assets. And the reason I've used harmonized and not basically uniform, you cannot assume that all geotechnical assets, and when I say all geotechnical assets, for example, slopes versus retaining walls, these are both geotechnical assets, but they have a totally different behavior. They serve different purposes sometimes. They have a different condition evaluation process. However, having a harmonious process where these different assets can speak to each other and your condition scales can at least translate to each other, not necessarily be on the same condition scale, but they can translate to each other to a point that you can say, okay, a slope at that condition state could have lower levels of risk compared to a retaining wall in that condition state. So having a harmonious condition evaluation process is a critical point in coming up with more encompassing and more inclusive GAM program, because currently many agencies have discrete GAM programs, a small program for slopes, another program for retaining walls, which is totally understandable because these are different types of assets. But if we want to look at a GAM program at the network level, and we're talking about the agency level, I'm sorry, then we should start thinking of encompassing multiple geotechnical assets. The second aspect is, again, going back to what data is needed and what is sufficient. At this point, the data collection is a little bit extensive, and we have point clouds sometimes with millions of data points. Do we really need all of that? Or do you need a single point to represent deformation? And other asset management programs went through that process. For example, pavements. At the early stages for tracking, for example, was visual inspection. Then people moved into collecting images. And now there are autonomous algorithms that can extract information and summarize it in terms of how much cracking do we have. Do we need all the details and the images? It's good to have a database at some point, but it's not necessarily needed to assess the condition for these pavement sections. Same thing applies for geotechnical assets. How much do we need? What information is needed? However, that question will be answered after going through multiple iterations, or at least thinking about the ultimate goals that we need and the processes and what goes into each process, and accordingly what data is needed. Data management and governance. We've mentioned that before, but I would like to re-emphasize that. Data management and governance will be an important aspect of geotechnical asset management, especially that we have different programs and different geotechnical assets and different databases in some cases. Having a proper data management process will help agencies also in their knowledge management. And knowledge management is basically making sure that the knowledge one person has is transferable to other people and can be used once that person, for example, moves out of the program or into another program. So data management and governance is an important aspect. Effective communication is a very critical aspect as well. GAM programs, especially at this stage, are still early in the process. And getting the support from multiple offices is critical and important. So effective communication of the results and what you want to share regarding the GAM benefits, how much cost effective is that, is very important and critical. And finally, building the foundations for future success, making sure that we have thought about all the details and we have outlined the processes early on and accordingly identified what data is needed, data management practices, and all these other aspects early on in the process is very important. And with that, I'll conclude my presentation and go back to Jerry. Back to you.
Well, thank you, Ahmad. That was very smoothly delivered for a wide range of diverse but related topics. And I'm sure a number of people, when they look at the PDF version of the presentation, will digest it a bit further than they can, even though your delivery was excellent. So we've already received a few questions, which we'll get to just in a minute or so. And Ahmad will do his best to answer as many questions as possible in the available time. Next slide, please. I'd like to first share, as we always do, some up-and-coming webinars that we have for you. If you're new to the program, we're embarking on the 4th year of the monthly ARA program in February of 2023. The next presentation is a bit earlier than usual in the month. It's on Wednesday, December the 14th. It's entitled Experimental and Numerical Performance of Cement-Bonded Geomaterials, which are stabilized with plastic waste. And our presenter is ARA employee, as all of our presenters are, Dr. Tanzila Tasbasum, and she's an expert in that particular area, as well as several other emerging areas in geotechnical engineering. We have many more exciting topics for you. We have presentations lined up through March of 2023. The program will continue past that date. We generally try to market and identify presenters 2 or 3 months in advance. Next slide, please. Now, I'd like to get to the Q&A program, as I mentioned. And again, if you have not already, we'll try to address as many questions as we can. If we do run out of time, what we generally do, and Ahmad has agreed to follow suit, as all of our presenters have, for the next 48 hours or roughly 2 days on this particular topic, you see Ahmad's email address shown here. If you have formulate questions that are follow-up questions or initial questions you didn't have time to present or we didn't have time to address, please send him an email. He'll do his very best to help you out as best he can. Well, we've got a question from Derek, and it's related to slide 33. And might using standard deviation dollars of failure as a parameter that is optimized present a bias that tends, a bit of a long question here by Derek, forgive me, that tends to present a bias that tends towards addressing condition states with smaller standard deviations like good condition or smaller deviations like replacement. I can repeat that, Ahmad, if that's helpful.
Nope, that's understandable. That's an excellent question, and that's actually, again, a limitation when it comes to basically selecting the proper parameter. I totally agree that generally speaking, when we're talking about standard deviations also, assets that are basically in the worst first, it will get you back at some point to the worst first condition, or approach, I'm sorry, because assets with basically progressive deterioration have more certainty that they will fail in the future compared to assets that are in a basically mediocre condition. So I totally agree that this is probably not the best selection of parameter. And we have looked at other parameters that are actually much better, but again, forgive me, and I tried to pull this from one of the simulations. But yeah, I totally agree with that assessment.
Okay, the next question is from John. And first, John, thank you for providing and presenting this program. John's question is, how would you superimpose external factors such as climate change, increasing groundwater, or surface water levels?
Again, another excellent question, and that would be basically in the performance prediction model, that one aspect of it. So part of the basically performance prediction models is to have multiple variables or outsider variables. And we have been looking actually specifically at incorporating also resilience. So one idea or one thought that we have been discussing and trying to look at is to incorporate that also in the condition assessment stage. So a condition of an asset, how vulnerable that asset would be. And that's obviously not a new concept, but including that in the condition assessment stage and quantifying the probability of having an external extreme condition, for example, or change in condition. It should not necessarily be an extreme condition, but for example, changes in groundwater levels, and incorporating that in the models, the performance models, that would help in addressing part of that question.
Okay, thank you. The next question is from Lauren. And Lauren, it's kind of an all-encompassing question, but briefly, could you kind of address how non-destructive evaluation technologies and remote sensing could help with GAM programs?
Definitely. Non-destructive evaluation can help in the risk-based, again, data collection process. And non-destructive evaluation at this stage, even though it has been out there for a while, but when we're talking about network-level applications, it could be a little bit a different question. So once that non-destructive evaluation is applicable at the network level, it could help in assessing the risk associated with some of the assets to go back and do further investigations. Because in many cases, non-destructive evaluation does not always give direct engineering measurements. It could give you an indication, for example, of a zone that collects water in the back of the wall, for example. And that would basically help in going back and assessing that specific slope or roll and so on. So that would be one of the approaches to incorporate non-destructive evaluation.
Okay, thank you. And we've got a few more minutes, 5 minutes or so for additional questions. The next question is from Ali. And Ali would like you to further explain what you mean by harmonized condition evaluation.
Awesome. So harmonized condition evaluation, as I indicated, is basically coming up with a scale that is transferable. It's not necessarily the same condition scale. It's not necessarily going, all assets will fall under that same scale. In pavements, for example, you can come up with different PCIs depending on the type of pavement. So you can have a PCI for basically flexible pavements. It's derived in a different way than the PCI of rigid pavements, but they both eventually communicate and speak to each other. And they both reflect basically the overall condition of assets. So having some kind of a scale where different assets can speak the same language eventually is important. And one approach to do that is basically to look at, there are different approaches. For example, deduct approach, or you can come up with a deduct process depending on different conditions, again, for different assets, but eventually they will give you a deduction rate for a scale, for example, a uniform scale. But again, keep in mind that it's not necessarily going to be the same scale, but harmonized means that they can translate to each other in terms of risk, for example, impact on network performance, and so on.
Okay, the next question is from Sarah, and Sarah, I'd like you to comment on what type of data would be collected using remote sensing technologies such as LiDAR or using a UAV.
That's an excellent question, and going back to the data aspect of this, basically the type of data depends on the goal of the program. So at this stage, a lot of the superficial data, let's call it LiDAR data, UAV data, is mostly, or not mostly, let me revisit that. It's focused on assessing where these assets are and looking at the deformations and maybe their general condition from the surface. So it could actually serve at some point as an alternative to basically engineers or staff going out and collecting data visually on the ground all the time. So you may collect UAV data, for example, and look at it in the office. And that process itself needs validation, obviously, and there will be requirements on how to collect that proper data so it can be representative of the condition. One thing I wanted to point out when we're talking about data for GAM programs is a little bit unique compared, for example, to PAVES, because a failure of one of the assets may be very significant and lead to basically safety implications and very significant cost implications. So looking at the assets collectively and forgetting about the individual assets can be a mistake, actually. And accordingly, the type of data, or using UAV technologies, LiDAR data at the network level, should be carefully designed to account for major individual assets and not just give an overall indication and exclude the performance of individual assets.
Okay, and we have time for one last question. And the question, I can't identify who is asking it. However, the question is, you established that in defining the assets to be included in GAM, risk assessment would be critical since all the assets cannot possibly be managed. Which important questions would you consider in arriving in this risk assessment framework?
Another excellent question. So the questions could include, first of all, basically the consequences of a failure. So how critical is that asset compared to, for example, other performance applications? So that's a big question to ask. The other question is basically the economic impacts and the extent of that impact. So going back to the example of basically small retaining walls, if they are extensive all over the place and they will lead to some major economic impacts, then it may be more necessary to ask these questions. And for both cases, a quantifiable measurement would be ideal. So economic impact, safety impacts are the most critical. Also, one important aspect that we should think of all the time is basically the communities surrounding these assets. So a lot of these assets are adjacent to some community. How much would that affect the community? That's also something to ask. And that question is a very tough question, actually, because the measures or quantifiable measures related to community are very, very challenging. But also that's a very important aspect to ask. The other thing to ask when we were talking about risk is basically the frequency of that event to occur. And the frequency in terms of probability, or basically, again, and at the individual level, the probability of failure, or the frequency at the network level. So these are some of the basically major questions to ask. But when we're talking about risk-based data collection, focusing on the probability at the individual asset would be more critical, because you want to assess how probable is that asset to fail, given that we have observed 1 and 2 and 3, and should we go back and look at it.
Well, unfortunately, we've run out of time, and we do have some additional questions. I want to thank everybody for their questions, and if we didn't get to your question, as I mentioned previously, Ahmad has agreed to answer questions for the next 48 hours via email. We just ask, if you're asking a question that we didn't get to, or you think of a question that you'd like to submit, just put it in the form of a technical question and not make it consulting related or project specific related. I think everybody appreciates why we make that comment. Next slide, please. Just on behalf of ARA, I want to thank everybody for joining us today. Today's presentation is being recorded, and a link will be available on the ARA Webinar Wednesday website early next week. We'll also send a PDH certificate to all the participants verified by our attendance report as being present for the entire webinar program of 1 hour. A copy of today's presentation will also be included, and please allow us 3 weeks approximately to receive your certificate. Next slide, please. And really the final slide, I believe, is ARA is an outstanding company. I'm embarking on my 10th year with ARA starting on January 4th of 2023. It's an outstanding company. We've had an excellent year, both financially and technically. Both of those go together. Engineering and science for fun and profit is one of our mantras. We're always looking for great people. If you're interested in employment opportunities that currently exist within ARA's transportation and infrastructure offices, you see on this slide, just send us a brief resume and contact information, and we'll follow up with you in the near future. Please remember the December 14th date, a bit earlier than usual. I want to thank you all for joining again today's program. May God bless you.